Hi, good morning everyone. My name is Shatanai and today I will present my course project which is called Analyzing Network Traffic Log to Detect End-User Activity using Python. This project focuses on using interpretable statistic and clustering method to detect DDoS related anomaly in the dataset called CIC IDS2017. The presentation will cover the problem context, research question, data and method, key result, limitation, and implication for security operation, followed by a live brief code demonstration to show how the pipeline run end to end. Modern enterprise network face an expanding range of threats, including high-volume DDoS attack and stealthy data exfiltration, often hidden within encrypted traffic. In these environments, security analysts need detection approaches that are not only accurate but also transparent enough to support alert, triage, and rule tuning in the Security Operations Center. This project used a dataset called CIC IDS2017, which was designed to resemble real network conditions with benign traffic and multiple contemporary data types, including DDoS. The core idea is to evaluate whether relatively simple flow-level analysis of variables such as byte per second and packet per second can still service anomaly effectively without relying on complex deep learning model or payload inspection. Many early intrusion detection datasets such as DARAP98 and KDD99 have important limitations. They do not reflect current traffic pattern, they lack diversity in attack type, and they often have unrealistic ratio of benign the malicious traffic, which can cause model training on them to perform poorly in production. This dataset that I'm using for this project have addressed many of these issues by capturing real traffic over multiple days, including benign behavior and a broad set of modern attacks such as DDoS, bot scan, and brute force attempts. In today's network, payload inspection is increasingly constrained by encryption, so per packet deep inspection is not always feasible. As a result, flow level metrics like byte per second, packet per second, and service port remain crucial signal for anomaly detection because they are not only observable and can be monitored at scale in operation environment. This project addressed two main research questions. First, how effectively do univariable accurate base outline detect and multi-variable DBSCAN cluster model apply for a flow byte per second or flow packet per second, identifying DDoS flow in the Friday portion of the dataset that I'm using, which is called CIS IDS 2017. Second, do visualizations such as histograms, scatter plot, and destination plot distribute make a detection result more interpretable for security analysts? The working hypothesis is that DDoS flow will appear as high throughput outline occupying spare region of the feature space and concentrating on a relative small set of service port. If this is correct, then simply rule based on throughput and port pattern should be able to flag suspicious flow in this way that is easy to explain and tune in practice. The analyze focus on the dataset called Friday Walk Hour Afternoon DDoS file, which is from the dataset file that I use, CIC IDS 2017. And this file was generated by CIS flow meter, which educate packet into bi-direction flow and computing more than 80 traffic feature, including volume, timing, and flag-based indicator. For this project, the emphasis is on 4 interpretable variables. First, flow byte per second and flow packet per second as measure of throughput intensity. Destination pose is to represent the target service and label field that encode whether each flow is benign or associated with DDoS activity. These variables provide a compact but meaningful view of traffic behavior for anomaly detection. The pipeline is implemented in Python 3 using Anaconda distribution and Spider IDE, which support a reproducible script-based workflow suitable for research or teaching. The pre-processing phase first replaces any infinite value with missing value, then remove columns that are entirely missing, drop rows with excessive missingness, for example, more than about 30% missing entity. For the remaining numeric feature, the script uses median imputation, which is robust to skew distribution that are common in network traffic. The pipeline also removed duplicated flow to avoid bias, and it created log transforming version of the throughput variable to reduce write skew and improve the behavior of distance-based clustering method. Finally, it was standardized version of the key feature and compute using the scaling steps because DBSCAN is sensitive to feature scales and require comparable numeric range scale. The analytics stack combine widely used Python library to keep the method transparent and reproducible. Python and NumPy is used for data loading, cleaning, and transformation. Seaborn and Metaply generate the diagnostic plot exploratory visualizations. For modeling, scikit learn provide the standard scalar and DB scaling implementation, and SciPy is used to run static tests, chi-square tests of independent to relate cluster or noise label to the ground truth label, and the many-Whitney U-test is to compare throughput distribution between benign and attack flow. Together, these two prioritize interpretable and statistic groundbreaking than black box complexity. Now I will briefly demonstrate the Python script that implements the pipeline that described in the slides. Okay. At the top of the script, you can see the main library, Panda, NumPy, Panda and NumPy, and is for the data handling. Seaborn and Metaply is for the visualization. Scikit learn for the scaling and DBSCANs, and SciPy is for the statistic test. The configuration section is specific for the paths, to the Friday working hour afternoon day DDoS Excel file, CSV file, and the output directory is where all the figure for picture that's going to be saved, so the result are fully reproducible on the same data set. As you can see, this is a function called load and clean, which encapsulate the pre-processing steps to unload the Excel file, CSV file, replace infinite value with missing value, drop problematic rows and column, imputing median, removing duplicated, and add log transform throughput feature. Structuring the workflow into feature keep the code modular, readable, and easable to reuse in the future experiment. So I have already run the code in here, and as I run the code, the first it prints the basic information about the CSV file in the original shape. Then it applies the cleaning process and report the shape of the cleaning dataset. Next, it will perform exploratory data analysis by summarizing the flow byte per second, and then flow packet per second by generating the histogram throughput which will appear in the presentation slide later. After exploratory phase, the script will apply IQR outlining detection, the flow byte per second, and report how many flow fall outside the uh, interpretable range threshold. If it's then draw a random sample of 20,000 standardized the selecting feature, then it will run DBSCAN, the consoling output, including the number of observation labeling as noise, followed by a chi chi-square statistic and p-value comparing DBSCAN label with the ground truth labeling, and many Whitney Utah statistic comparing benign and attack throughout. These summary value and constraint will be educated results will be shown in the upcoming slides. So like I have after completing the code, it will show like the script, the photo have been created, and the where it's stored, it will be showing in the output, and I will show you the photos. It's being outlook. So these are the three main figures in the code. The first is a histogram of flow byte per second. Uh, yeah. Okay. Flow byte per second, which highlighted the heavy write tail and the concentration of benign traffic to relatively low throughput value. The second is a DBSCAN scatter plot of flow byte per second versus flow packet per second for the 20,000 flow sample, dense region corresponding to a typical traffic and spiring cluster of high rate flow labeled as noise. The third figure will show a bar chart of the most frequent destination port, which emphasize the prominence of ports 80, 53, and port 443 in the observed traffic. Together, these figures illustrate that the implementation pipeline, loading, cleaning, outlining, detection, cluster, and visualization faithfully realize the methodology described in the report, and the slide can be to reproduce the result. Going back to the slides. Okay. The exploratory analysis showed the flow byte per second is strongly right skew, with the most flow concentrated with relatively low throughput, but with a long tail extended to very high value that frustrated of DDoS traffic burst. Applying a log transformation to a variable produce a more semantic distribution, which help the clustering algorithm better distinguish normal from abnormal region in the feature space. In this dataset, a substance fraction of flow in order of 10 of the percent fall into the IQR defined outlining region, which reflect the fact that the file is attacked in region rather than purely benign. This pattern supports the idea that throughput metrics are informative discriminator between benign and DDoS flow in the particular scenario. Using the IQR rules on the flow byte per second to reproduce a flag to sizable subset of flow as high throughput outline, which is constant with the presence of the many flow in the DDoS focus file. When DBSCAN is applied to a standardized 20,000 flow sample, the algorithm forms dense clustering corresponding to low rate background traffic and labeling high rate spare flow as noise, which is expected behavior for normal point in the density-based cluster framework. To connect these unsupervised results with ground truth, chi-square test of independence is conducted between DBSCAN noise label and the database pinging versus attack label, and the result p value is highly significant, indicating that noise points are strongly enriched in attack flow. Similarly, a man-Whitney U-test compared throughput between pinging and attack flow shows significantly high median throughput for the attack class, reinforcing the conclusion that the chosen feature have meaningful discriminatory power. Destination port analysis revealed that the flow are heavily concentrated on a small number of service ports, particularly port 80, which is HTTP. Port 53 is for the DNS, and port 443 is the HTTPS. When together account for a large share of the traffic in this file, the pattern aligns with typical enterprise usage where web and DNS service dominate, but it also shows where attackers focus their effort when generating DDoS traffic. From an operational viewpoint, this suggests that monitoring surge in flow count and throughput to a small set of critical ports in combination with anomaly signal from throughput-based detection can provide early warning of DDoS behavior when payload content are encrypted or unavailable. These insights can support rule tuning and dashboard design in Security Operations Center. Overall, the result form a coherent narrative. DDoS will tend to occupy the high throughput tail of the byte per second distribution, then appear as spare point in the joint space of byte and packet per second, and they are concentrated on limit set of destination port. DBSCAN noise label effectively prioritize this unusual flow with IQR-based rule providing a simple baseline for flagging potential anomaly. However, translating these findings into reproduction require configure collaboration. Global threshold derived from an attack-heavy dataset like this dataset might lead to excessive false positive in real network where benign traffic dominates. Therefore, threshold and cluster parameter will need to be tuned to the prevalence of attack and typically traffic pattern in a given environment. In comparison with more complex supervised machine learning approach such as gradient boosting and surveillance apply to the same dataset, that the method here are intentionally simple, more interpretable. This is an advantage for security operation where analysts need to understand why an alert need to understand why an alert was raised and how to adjust the rule in response to evolve threats. At the same time, there are several important limitations. First, this Excel file, Friday DDoS attack file is like attack heavily, so the proportion of outlining and noise point may be higher than the typical producing network, which limit direct generalization of threshold. Second, this analysis focus on the narrow feature set and does not exploit richer contracts such as source IP behavior, session history, or temporary pattern between flows. Future work could incorporate additional timing feature, adopt supervised evaluation metrics like F1 score, and extending the pipeline to streaming data, enabling online detection rather than purely offline analysis. In summary, this project demonstrates the relatively transparent Python-based method combining accurate outline detection, density-based clustering, and straightforward visualization can effectively surface DDoS-related anomaly in the CIS, the dataset that I use, CIS IDS 2017, using only a small set of flow-level features. The finding reinforcement the value of benchmark dataset, such as the dataset that I use, highlighted how reproducible code-driven workflow can be bridge the gap between academic research and operational security practice. Looking ahead, integrating these interpretable technique with supervised model and streaming architecture could improve detection performance while preserving the clarity that security analysts require. Here are the references I use, list of references and EPA format. And thank you for your attention. I'm happy to take any question. You can contact me from my Gmail or LinkedIn. Yeah, thank you.